Solving exponential equations, Objective 8.9. In this objective, we're going to be looking at solving equations that have an exponential term in there. And basically there are two methods to use when you have that type of equation. And so those two methods make up our two objectives for today. We're going to try to use equivalent exponents as one method for solving this type of equation, and we're going to learn how to use logarithms as another possible method for solving exponential equations. So let's take a look at example 1, and in this example we want to try to equate exponents. So what does that mean? Well, take a look at our equation here. We have 4 to the 3x, and that's supposed to be equal to 8 to the x plus 1. So the first thing you want to ask yourself is, can the bases of these two exponents be rewritten as exponents with the same base? Okay, so can the 4 that's the base in this exponent and the 8 that's the base in this exponent be rewritten so that they would have the same base raised to some exponent? And the answer is yes. The 4 can be rewritten as 2 squared, and the 8 can be rewritten as 2 cubed. Now notice the 3x is still out here as an exponent, and the x plus 1 is still out here as an exponent. So we haven't really touched those at all yet. We're just rewriting the 4 and the 8 so that we get matching bases. Once we've done that, then we want to use properties of exponents to simplify. So hopefully you remember that when you take a power raised to another power, that means we can multiply those powers together. So here, taking the 2 times the 3x gives us the 6x right here. And when I take the 3 times this x plus 1, I have to distribute and make it 3x plus 3. So now I'm saying that 2 to the 6x power has to be equal to 2 to the 3x plus 3 power. Well, the only way that these two sides can be equal to each other, now that they have the same bases, is if the actual exponents are equal to each other. And so that's all we really need to solve. How do we make the 6x from this exponential side equal the 3x plus 3 from this exponential side? Well, now it's just a linear equation. So now we just solve like we know how to do. Subtract the 3x from both sides, divide both sides by 3, and we get x equal to 1. Now, let's make sure that that actually works, so let's check that out. If we substitute the 1 in for x in our original equation, remember we always go back to the original, that means we're going to have 4 to the 3rd power on the left side and 8 to the 2nd power on the right side. And when we work both of those out, we see that they both equal 64, and so our solution of x equal to 1 really does work. Alright, let's take a look at another example. Here we're asked to solve the equation 2 to the x equals 7. So you can ask yourself the same question. Can the bases be rewritten as exponents with the same base? However, the answer in this case is no, they cannot. So in this case, we're going to use our other method, which is taking logs of each side. So I'm going to take either the log log or the ln natural log of each side of this equation. Logarithm is just a function. It's an operation, just like squaring, just like adding. It's something that you can do to something else. So we're going to do this to both sides of the equation. Which one you choose doesn't really matter in this case, but you do want to choose one of these two because these are the two that have buttons on your calculator. So I'm going to choose to take the log common log of each side of the equation. What that does then is it allows me to use the power property for logarithms to rewrite the left side by bringing this exponent down in front and multiplying it by the log of 2. And what that allows me to do then is to sort of access this x. As long as the x is up here in the exponent spot, I can't really get to it. I can't solve for it or get it isolated. But by rewriting it using our properties, now it's down here where I can work with it. And because I now have x times the log of 2, the log of 2 is just a number, and so I can divide both sides by that number. So I would get x equals the log of 7 divided by the log of 2. Now, if you were doing a quiz or a test where you are not allowed to use calculators, this would be your final answer. This would be as far as you could go, and you would leave your answer in this form. However, if you have a quiz or test where you are allowed to use a calculator, then you can go ahead and plug this in and find that x is going to be approximately equal to 2.807. Be careful with this. Depending on the type of calculator you have, when you punch this in, you may need to make sure that you're putting parentheses in around the 7 before you divide by the log of 2. A lot of times the calculators will set up and they'll put log open parentheses. You'll type 7, but if you don't close the parentheses before dividing, you're going to get a different answer. So just pay attention to that and make sure you're doing this carefully. If we check this, we're going to do more of an estimate to check because 2.807 is kind of an ugly number to try to use as an exponent. So in our 2 to the x equal to 7, we're going to use a 3 because if I round 2.8 up, it would be close to 3. So by putting 3 in for x, we can see that 2 cubed would equal 8. And since the answer I was looking for was 7, the fact that 8 is fairly close to 7 makes it seem like 2.807 is a pretty reasonable answer. So we can feel pretty confident that this is indeed the solution. All right, let's take a look at another example of this. Here's a case where we're taking 10 to the 2x minus 3 power plus 4 equal to 21. Now, before you can ask yourself any questions about rewriting bases, you need to isolate this exponential term. So the fact that we have this extra plus 4 on here means that we need to move that over to the other side first. So we'll subtract the 4 from both sides to make it 10 to the 2x minus 3 power equal to 17. Then you can ask yourself questions about rewriting bases. In this case, we cannot rewrite our numbers to have the same base, and so we're going to take the log of each side. And in this case, we do specifically want to use the log log because we have a base of 10. And by using the log common log, we know that also has a base of 10 right here. So again, using properties, we know that when the bases of our log and our exponent match, they actually just cancel each other out, and what we'll have left is just the exponent from this term. So the 2x minus 3 now is what's equal to the log of 17. Now I can go through the steps to get x isolated. And so I'll add 3 to both sides. Notice it's still the log of 17 plus 3. This does not become log of 20. Okay, it's log of 17 plus 3 and then divided by 2. And so again, if you're working on a quiz or test where you do not have a calculator, you would leave your answer in this form. But if you are allowed to use a calculator, then you can work it out and you should get approximately 2.115. Again, the check for this should be just a quick estimate. Since this is about 2, just a little bit more than 2, we're going to use 2 as our x to see what we get. So 2 times 2 is 4, minus 3 is 1, so we're looking at 10 to the first power plus 4. That's just going to be 10 plus 4, so that's 14. And since 14 is relatively close to 21, we can be pretty confident that 2.115 is probably going to be the correct solution. Right, so those are two different methods that we have for solving exponential equations. Why don't you take a moment now and see if you can use one or both of those methods in solving these two equations. Pause the video for a moment while you work them out, and then come back when you're ready to check your work. All right, so here's what your work could look like. In the first example, since we have 10 to the 3x minus 4 power on the left and 0.1 on the right, we could rewrite this decimal as 10 to the negative 1 power. And so that would give us the same base and would allow us to just set our exponents equal to each other. 3x minus 4 equal to negative 1. Now if you didn't notice that, you could still go about this using the log of each side and working it out that way. But once I set 3x minus 4 equal to negative 1, it's just a matter of adding the 4 and then dividing both sides by 3 to get x equal to 1. And when we substitute the 1 back in, the 3 times 1 minus 4 gives us negative 1, and 10 to the negative 1 is 1/10, which can be written as the decimal 0.1. So it does work. In the second example, we have negative 5e to the negative x plus 9 equal to 6. So the first thing we want to do is get this e to the negative x all by itself, which means we'll have to subtract the 9 first and then divide both sides by the 5. So we get e to the negative x equal to 3/5. Now we're ready to decide whether to equate exponents or take logarithms of both sides. Well, obviously I'm not going to be able to change this into the same base, so I'm going to take logarithms. And in this case, I specifically want to use the ln natural log because of this base e. By taking the natural log, which remember also has base e, that allows me to cancel out the ln and the e and just be left with the negative x. So that comes down here to continue with my problem, and that is what has to be equal to natural log of 3/5. So when I divide both sides by negative 1, I get x equal to opposite of the natural log of 3/5. And again, without a calculator, you would leave it this way. With a calculator, you would make that a 0.511 because the natural log of 3/5 is negative, and then the opposite of that becomes positive. Alright, so hopefully that gives you enough information to be able to work on your 8.9 practice in the book. If you have any doubts about any of the things you've seen in the video, please make sure you ask about them during class. And when you are finished with your practice, make sure you show it to Mrs. Gordon so she can check off this objective for you. We'll see you next class.